So section 10.6 is going to talk about conic sections in polar. So let's remind ourselves of what the conic sections are and can look like. You've got 4 different conic sections: a circle, ellipse, hyperbola, and parabola. They're all made from the intersection of a plane and 2 cones placed tip to tip to each other. I always find it amusing, the image of some early Greek mathematicians on an island someplace next to the ocean and sitting around saying, hey, I got this great idea. Let's put 2 cones tip to tip and see what kind of intersections we get with a plane. But those intersections in polar all have one of 2 forms. Well, a total of one of 4 forms, really. And those forms are going to be like this. Now, depending on your choice of the plus or minus, or your choice of the sine or cosine, you're going to get different functions. If you choose a positive value underneath there and a cosine, then you're going to get this graph right here. If you choose a negative value and a cosine, then you're going to get this graph right here. And then there's a couple more choices as well. You could choose a positive value and a sine. That would give you this one right here. So the positive value and the sine. And the last one would be a negative value and the sine. It's going to give you this graph right here. Now, displayed in this graph are a bunch of parabolas, or at least what looks like it could be parabolas. Depending on the choices of E, depending on the choice of E, you could get either an ellipse, a parabola, hyperbola. It depends. So let's take a look at that. Now, that choice is going to depend on the eccentricity. This is the same eccentricity we saw in section 10.5. So let me remind you of eccentricity here. Let me go back here and let's see, shut this off. Come back here. So as I change the dimensions of this, this becomes more and more eccentric. The eccentricity is going to be a ratio of this longest side to C. So you can see the eccentricity down here is getting higher and higher, meaning it gets narrower and narrower. It has the same interpretation for us in section 10.6. Let's see what happens when we change that value of E. There's 3 different things that you can get. So right now I can't use E because E is reserved for 2.71828, etc. It's reserved for a constant, so I chose C instead. And let's change the eccentricity here. Now what you'll see is a change in the shape of my ellipse. As I dial it down towards 0, this gets closer and closer to the shape of a circle. But as I increase it, you get this thing happening. And eventually, this is going to explode here. Why is it going to explode? Let's do a little thought experiment. When this becomes 1, well, a little bit more. When it becomes 1, all of a sudden, it's possible for this denominator to be 0. Remember, sine and cosine vary between -1 and 1. So for the right value of theta, if this was a 1, then 1 plus cosine of theta could actually turn into a 0. And at that point, things blow up, and you get exactly a parabola when c equals 1. If you go past that, then you get the shape of a hyperbola for c greater than 1. So depending on your choice of that parameter, you're going to get one of those 3 shapes. Now, I want to point out one thing about that choice of parameter. In all of these, this bottom left number here in the denominator is always 1. So that's going to be something we're going to have to pay attention to in order to figure out in these problems sometimes what is E, what is D. So it's always equal to 1. So you got those 4 different shapes. Their directrix is going to depend on, you know, your choice of D relative to your choice of E and the choice of this equation. For something like this, you've got a vertical line of a directrix to the right of your parabola. You could have one to the left or above or below. It's just going to depend on the particular choices that you make. So let's see if we can't figure out what's going on with example A. It says write a polar equation of a conic with a focus at the origin and the given data. Our eccentricity is 1/2 and the directrix is 6. So that's telling us a couple things that we should probably take note of. First of all, that E is 1/2. This is telling us that x equals 1/6 is the equation of the directrix. But that also tells us something else in a different way. Does anyone know what that extra little piece of information is? That's going to be your value for D. D equals 6 is essentially what they're telling you. Now, if this is going to be something positive, then this is going to have to be something that opens to the left. We're going to have a shape like this. So overall, the equation that we're going to work with is going to have this form. R equals E times D over 1 plus E times cosine of theta. So let's do that. R equals 1 plus 1/2 cosine of theta. And in the numerator, I have E times D, so it's going to be 1/2 times 6. You can clean that up a couple steps. You can write it as 3 over 1 plus 1/2 cosine of theta. And I'm fine with that. I kind of like that because I've got the 1 here, and I know that this has to be the eccentricity, and then I can figure out that D must equal 6 from this. Sometimes you'll see the book clean it up like this. They'll get rid of this 1/2 down there in the denominator if they multiply everything by 2. So I guess the advantage of this is that you can actually see what D is in the numerator, I suppose. So you got 6 over 2 plus cosine of theta. So that's an alternate form of this, but to me, I'm just as happy with this one. So I'll take this or this as a final answer in a problem like this. Yay. And that's it. That's all they're asking for there, is to figure out what kind of equation this would be, what it would look like. You can graph those in polar on your graphing calculator. We'll do that in a little bit with example C. For right now, let me move on to example B, unless there's something about example A that you're a little unsure of. Write a polar equation with a conic with a focus at the origin. By the way, I should have mentioned that with all these, you're going to have a focus at the origin. One focus at the origin. For ellipse and hyperbola, you're going to have 2 foci. Write the polar equation of a conic with the focus at the origin and the given data. Eccentricity of 1.5, directrix of y equals 2. So first things first, what kind of a conic section does this have to be? There's just no choice about it. If our eccentricity is 1.5, what's that telling us about our conic section? You mean? No? Curtis? What kind of conic section does this have to be? Some help?
A hyperbola.
Yeah, so going back up to the top here, if you have your eccentricity is less than 1, it's an ellipse. If it's equal to 1, it's a parabola, and greater than 1, it's a hyperbola. So because this is greater than 1, we've got a hyperbola. So it has to be a hyperbola. Which form of the conic section from up above should we use? Now keep in mind we've got a directrix of y equals a positive 2. What's that line going to look like? Is that going to be horizontal or vertical? Marlon? Y equals 2. Is that graph going to be horizontal or vertical?
It's going to be horizontal.
Good, it's going to be horizontal. All right, so of these 4 forms, we can eliminate 2 of these, right? It's not going to be something like this. It has to be one of these forms. Now, because we've got a directrix with a positive value for D, we're going to choose this form. So it's going to be R equals E times D plus, or divided by 1 plus E times sine of theta. So R equals E times D over 1 plus E times sine of theta. Okay. What's the value of D that should be used here? Yeah, D equals 2. Let's put all that together, see if we can't figure out our equation. So it's going to give us R equals 1.5 times 2 over 1 plus 1.5 sine of theta. And that could equal, or that does equal 3 over 1 plus 1.5 sine of theta. Now again, I'll give you a different form because it seemed like the book sometimes likes to get rid of the fractions here. We could get rid of the fraction here by multiplying by 2 over 2. So an alternative form would be 6 over 2 plus 3 sine of theta. So either one of those would be fine for an example like this. Nice, nice. Let's move over to example C here and keep going. For example C, we're going to have to do some work with our graphing calculator, but I want to figure out a few things first. In fact, the first thing here is what's the eccentricity? Can I say the eccentricity is 4? Ooh, not yet. Why can't I say the eccentricity is 4 just yet?
E times D.
Has to do with this number here.
Is it 4? Oh, it should be a 1.
This has to be a 1 before you can figure out what the eccentricity is. So let's go up here. R equals 4 over 5 plus 4 minus sine of, yeah, there should be a minus there. 4 minus, or minus 4 times the sine of theta. 4 times the sine of theta. I need to make this a 1. So if I want to make that a 1, I can divide everything by 5. I'll do it like this. I'm going to multiply in the numerator and denominator by 1/5. So I'm multiplying by 1/5 over 1/5. What's the net effect of multiplying by 1/5 over 1/5? When you multiply by something like this, what does that reduce to? 1. So I'm not changing the value of anything. I'm just making it look different by multiplying it by this peculiar form of 1. I'll wait while you get out your graphing calculators. What's on top? Just kidding. Could be 4/5. How about in the denominator? What's in the denominator? Yeah, 5 times 1/5 is going to be a 1 minus 4/5 sine of theta. Brandon G. What's the eccentricity?
4/5.
Good. Eccentricity equals 4/5. Brandon B. If the eccentricity is 4/5, what kind of a shape is this going to be? Parabola, ellipse, or hyperbola? Feel free to look back on your sheet. Yeah, has to be an ellipse. If the eccentricity is less than 1, has to be an ellipse. So nice. Now what I want us to do is I want us to graph this. So we're going to put that into our graphing calculators. You should be in polar mode. So if you take a look here, right there it says, no, that says float, sorry, normal, radian. All right, well, let's take a look here. I'll make sure I'm in polar mode. Yeah, I am in polar mode. I guess I expected it to be reflected up here. I guess it's not. Anyways, you click the mode key, you cursor over to the right, press enter when you're on polar. Then when you click the Y equals key, you get something that looks a little different. You're asked to put in an R. So we want to put in a fraction. I'm just going to hit the alpha key, then the X key. That gives me a nice horizontal fraction, 4 divided by 5 minus 4 sine of theta. Where do I get the theta? Well, when you're in polar mode, when you press the X key, it actually gives you a theta. For the window, generally speaking, a good setting would be to do this from 0 to 2 pi in terms of your theta. So that's what I've got here, 0 to 2 pi. When you press the enter key, that 2 pi is going to disappear, and you're going to be replaced by the decimal value for pi. Now I've got theta step as 0.001. For yourself, you might want to do theta step as 0.1. Might make it a little bit faster on your graphing calculator. The processor speed on those things seems to be a little bit slow. Now looking at these graphs, it's kind of tough sometimes to figure out, well, where's this going to graph? What's it going to be? So we've got a little workaround to help figure out where we should graph this, where we should set the rest of our window settings. What is that workaround? Zoom 0. Yeah, zoom 0. Now zoom 0 is not going to be flawless, but at least it gets us started. Zoom and then 0 is really zoom fit. You should get something like this, but this is kind of exaggerating things a little bit because it's using the extra space on the x-axis, and the x-axis is already scaled bigger than the y-axis. So, to get a better look at that, you can hit zoom 5. That'll square things up. That's a better representation of what this looks like. It's taller than it is wide. That's okay. No big deal on that. So that last trick there was your zoom 5, and that gives you a better look at this. So we've got an ellipse here, and then we graphed it. So looking good on that. Are we okay with that graph on our graphing calculator? All right, let's stick with our graphing calculator for one more example here. We're going to graph this conic section. Kind of like the last one, I want you to start out, take a minute, and figure out what kind of conic section this has to be based on the form of the equation. If you're watching this later, pause it, watch, or try and figure this out yourself. Yeah, you need a 1 there before it can judge what the eccentricity is. It's saying exact same thing there.
Is not the numerator.
In the numerator, you have E times D.
Right.
So kind of like our last one, before we get busy deciding what kind of figure this is, what you can do is put it in the proper form. So let's take 5 over 2 minus 4 cosine of theta. We'll play the same game we did with the previous one. I'll multiply the numerator and denominator by the reciprocal of this term, that is by 1/2 and 1/2. When I do that in the numerator, I get 5/2 over 1 minus 2 cosine of theta, and that's my r. But the big thing there that I get is the eccentricity. Rain, what's the eccentricity there? 2. Good. So if the eccentricity is 2, what kind of conic section is this, Sophia? Yeah, that's going to be your hyperbola. Now, there's another way you could have told that was or guessed that that was hyperbola. What was it? Maybe look at the graphs below. All right, but don't really count on that because I can make these equations really, really ugly, and then you kind of need to do that. So let's see if we can't graph this. Now, there's a little something wrong with this graph. Can anyone tell me what's wrong with this graph? All right. Well, let's put that in your calculator while you let that thought percolate a little bit. Maybe you'll come up with something. So you don't need to put it in that nice little fancy form that we divided everything by 2 so that we could get rid of the 1 or the coefficient in the bottom left part of this. I'm just going to put it in as it is originally. So it would be 5. Let's see, put a 5 over here, and then a 2 and a 4. There we go. I think that looks pretty good. Oh, wait, I need to make that a cosine here, don't I? You know, I probably would have been better off just ditching the whole thing at this point. All right, last try, cosine of theta. Whew, there we go. So there's my equation. I'll play the zoom 0 trick again. And zoom 0 doesn't exactly work so good here, does it? You're getting something like that, and like, ugh. Now, chances are we're interested in this spot in here. So let's do a couple things to make this graph look a little prettier. So the first thing I want to do is I want to zoom in on this. Now I could spend some time and scratch my brain a little bit and think about, well, where do I want to zoom in? But rather than try and figure it out with numbers, let's figure it out with pictures. Hit the zoom key, then the number 1. That's zoom box. And when you do that, it puts a little cursor on your graph. And you're going to press, when you move that around a little bit, you're going to figure out, well, what do I want one corner of my box to look like? And that box is going to be your window. You press enter when you fix one of the corners, then you scroll up, and then you scroll over. So if I wanted to scroll to the right, I get a window to the right. but that would kind of be a boring graph. So I'm going to go to the left. And there we go. That looks like a better looking graph. So when you get those dimensions right, when you've got your viewing window where you want it, you press enter for the second time, and bam, it's going to zoom in to that graph. So that's looking a lot better. But there's still a problem with it that I'm going to ask you again of. What's wrong with this graph? It's got a lot of lines. All right, it's got lines all over it. And in particular, it looks like it's got the asymptotes of this graph, doesn't it? That's because of the way your calculator is trying to draw this graph. What your calculator does is it takes all these points from theta equals 0 to 6.28, and one at a time, starting at 0, and then 0.1, and then 0.2, it plots these points, and it tries to play connect the dots. And what's going on is you're getting a point way out here, and then the next point is way over here. It's trying to play connect the dots so that you get this artificial asymptote. It's not really part of the graph. If you don't want your graph to have those connected dots, then let's go over to another setting here. So a little inside trick here for you in terms of your graph. Go back to the y equals key. This time cursor to the left, and put that cursor on top of the equals key and press enter. You should get, well, let's see, no, sorry. I need to go one more. Go to the left of your R equals key, you'll get the various styles you can draw your graph in. Press enter here, and now you'll see the option to change the color, or if you scroll down one, you can change the style of the line. So I'm going to scroll around. That would help me watch it get traced out. I'm going to keep going until I get something like this, some loosely dotted lines. Now there's a couple, like one is more loosely dotted than the other one. Choose the first one, like this. I don't want a solid line here anymore. I want something like this. You should have the 3 dots. When you get that 3-dot choice, no longer will your graphing calculator try and play connect the dots. It's just going to plot the points, and that's it. So press the OK button. And I guess I got to press enter on my software here. And you see that it's changed the style of my graph. When you press the graph key now, all it's going to do is plot the points. So, wow, okay. It's not playing connect the dots anymore, but it's also not giving me those phantom asymptotes. Now, if you're looking at that like, yeah, that's not a really great picture, you could add more points by increasing or decreasing the size of theta step. Maybe make it 0.01. When I graph it there, yeah, that's a little bit more filled in. So, you know, it's a better looking graph here, and now that actually does look like the hyperbola that you should get. How are we looking on example D there? Doing all right? All right. Give me some feedback. Were those some good tricks, interesting tricks? Did you like ZoomBox? Had you seen ZoomBox before? ZoomBox is pretty handy. So, all right. That's going to take us to example E. So another conic section. How am I going to start out working with this one if I wanted to figure out its eccentricity? Yeah, multiply by 1/4 over 1/4. That's going to give me 5/4 over 1 minus 5 cosine of theta. Now there's a couple things that are going on here. We need to actually figure out what D is. Now, we haven't had to really do that before. And I want to take you back for a second to the very beginning of this. Remember what the form of the numerator is. The form of the numerator is E times D in both of these equations. So what I know in this one is E times D equals 5/4. But I also know something else that's going to help me solve for D. What else do I know that helps me solve for D in this one? Hannah? Yeah, E is 5, right? We know that E is 5, so we're in good shape there. That's a 5. Joseph, what kind of conic section is this going to be when we graph it? Thank you, sir. It's going to be a hyperbola. Let's put that 5 in here times D equals 5/4. And I'll put in the 5 here, like that. Now, a lot of you might be tempted to divide both sides by 5. That might get a little bit messier in terms of the arithmetic here. So let me suggest that we multiply both sides by 1/5. Can someone explain to me an advantage they might see in multiplying by 1/5? On the left-hand side, we get some nice simplification either way. But on the right-hand side, that should be a 1/5. 1/5. On the right-hand side, it's just a little easier to multiply this by 1/5 than it is to divide it by 5. I see people get troubled by that, so maybe do yourself a favor and multiply by the reciprocal. Those cancel. What do I get for D? Yeah, D equals 1/4. Now look at the form of the equation and decide where your directrix is going to be. With that form of the equation, what directrix are you going to get? So it has to be between one of these two, right? Because we have a cosine in the denominator. We got a D equal 1/4. 1/4 or negative 1/4?
Negative 1/4.
Yeah, actually, I think we've made a little tiny mistake here. Anyone else catching it? Yeah, the ellipse here, or excuse me, the hyperbola is going to have E equal negative 5. Yeah, so we're going to have to fix that a little bit. I'll put a negative in here and here. And when I multiply both sides by negative 1/5, I'll end up with D equals negative 1/4. So that's going to be the equation of our directrix. So D equals negative 1/4. This is going to have branches that open left and right from here, but one of them is going to envelop the origin at 0, 0. Okay. Yeah, D equals negative 1/4. That's the nice Cartesian version of our directrix. So that's something you can graph. Actually, I guess I should put it as x equal negative 1/4 would be the final answer for that one. A couple questions. Clyde? And then.
So on the form, it's when it's like the whatever directrix equals or over 1 minus. cosine theta, it's saying x equals negative d. So wouldn't in that case d still equal positive 1/4? And then just once you put it in Cartesian form, it's x equals negative d, and then x equals negative 1/4?
I guess what bothers me about that is that if I had negative of a negative, then that'd be positive, and that should be drawn to the right of the y-axis. But this is clearly to the left of the y-axis. So I'm going to stick with x equal negative 1/4. But you're right. That it seems like, well, wait a minute. Is d a positive or a negative? Well, the equation one way or another is d equals negative 1/4. X equals negative 1/4, because it has to be to the left of the y-axis. But you're right. That is a little inconsistency that disturbs me.
I guess what I was saying is I don't know if it's necessary for the
For
to be negative. Because if it's
yeah.
positive, then d does equal
Especially because in that top
put the
equation,
negative.
plus
Yeah.
or minus e, so it's like plus or minus e anyway.
Yeah. I'm thinking we could probably just have left e alone as a positive 5. And then we would have added d equals a positive 1/4. So yeah, no, I think you're probably right there. So the bottom line is that I think moving forward we should probably just not worry about the sign of e. E is just going to be positive. It's going to be something, greater than 0. Hannah, you had a question as well?
Kind of my question was, like, do we count the
Yeah.
sign in front of it? That what it is?
Yeah, so let's, d is 1/4. Let me get rid of the negatives there. I felt a little unsure about that when I was playing with it. So we'll get rid of the negatives there. Good. Appreciate you both. Thank you so much. We talked about planetary orbits earlier. And the planetary, the planets orbit the sun in this general kind of conic equation. So it's a times 1 minus e squared over 1 plus e times cosine of theta. E is going to be the eccentricity of your orbit. So we're asked to write an equation for the orbit of Mars. Now it says that, let's see, does it tell us here? Yeah, the major semi-axis is going to be A. Let me help you understand what they're talking about there. So major semi-axis is A. Let me draw a little ellipse here. Now I drew this hopefully long enough so that you can see that the major axis is along the horizontal direction. Now, typically speaking, if you had, for instance, x squared over a squared and y squared over b squared, if you had this formula, x squared over a squared plus y squared over b squared equals 1, because this is longer than this one, this direction, a has to be greater than b. So a, or 2a, is the length of the major axis. And that's because you have a distance of a here and a distance of a here to get to your vertices. So you have a total of 2a for the length of this. A itself is the length of half of the major axis. So that's why it's called the major semi-axis, or semi-major axis. Length of the semi-major axis. And in this particular problem, they're telling you that A is 2.28 times 10 to the 8th kilometers with an eccentricity of 0.093. Okay, so this is just a matter of plugging in some things. And I'm kind of running out of room here, and I want to use some more space. So let me just Move that over to here. Example F. So we've got R equals A, which is your 2 point, where is it? 2.28 times 10 to the 8th times 1 minus E squared. E is 0.093. And that needs to be squared. That squared needs to be inside the parentheses over 1 plus 0.093 cosine of theta. You could clean this up if you wanted to, figure out what fraction that it makes, multiply it by this, maybe give yourself a little easier time. It doesn't really feel worth it to me. I think that's good enough as is. I was going to leave example H for you to try at home. I'll let you work on example G at home. So let's work on example F, or example H, I should say, right here. And this has got a clever little trick in it that I'm not sure that you'd see very easily. So that's why I decided, let's maybe do this one here. Because there's something just kind of really cool about this one. And maybe just back off your writing for a little second and catch this on the notes if you're really interested in what's going on here. Because I've already got this pre-written out for us. And I just want to talk about it. So this is the form of the orbit for the planets. It's A times 1 minus E squared over 1 plus E cosine of theta. I want us to think about a couple things here. What's going to make this quotient the biggest? Well, this is going to be the biggest when the denominator is the smallest, right? When you're dividing by a smaller number, then the overall ratio is going to be bigger. If you had 12 slices of pizza, would you rather share it amongst 3 friends or 2 friends? Well, if you share amongst 2, then there's more for you, right? So dividing by a smaller number is going to give you a bigger quotient. So it's going to be biggest when this is smallest. When is this going to be the smallest? What makes 1 plus E times cosine of theta the smallest? Well, I guess it's when cosine of theta is negative 1. Because then you'd effectively have 1 minus E, right? So what value of theta makes this equal to negative 1? Say it's like, that's trig, man. That's no fair. You're going way back. Pi. All right, so at pi, this is going to be its smallest in the denominator. How about the other extreme? What's going to make this the biggest? At what point do I have cosine of theta equal to 1? 0 or 2 pi. 0 is the answer I was looking for, but 2 pi is acceptable. Now, let's put in those numbers here. So, for instance, this is going to be the largest when, or excuse me, the quotient is going to be largest when this is a pi here. Let's see, do I want to do pi? No, I want to do smallest first. So this is going to be the smallest. So the closest approach of a planet to the sun is going to be at its perihelion. So that's going to be when cosine of theta is really 1 plus, or 1 times E is E, 1 plus E. Here's the cool thing. 1 plus E and 1 plus E cancels. Notice I've factored the numerator, so I get that the perihelion, which is given to you in the problem, is A times 1 minus E. The aphelion is the opposite. This is when it's as far from the sun as possible. That's going to happen when this is a pi. If that's a pi, then E times cosine of pi is going to be negative E, 1 minus E. Factor this again, some similar cancellation, and we've got two equations here that are worth noting. You've got this first one right here, where you've got 4.43 times 10 to the 9th equals A times 1 minus E. And you've got another one here where you get A times 1 plus E. Now here's the clever trick. Let's bring those two equations together right here. If you add these two equations together, that's just going to give you 11.80 times 10 to the 9th. But on the right-hand side, the minus AE and the plus AE cancel, and you're just left with 2A. So you got rid of the E. You can solve for A. Once you solve for A, you put it back into one of your equations, say at the perihelion, you put in the value of A, and then you can solve for E. It's just a matter of, you got your value of A times 1 minus E equals this at the perihelion. You can solve, and you actually come up with a value that's very close to what you would get if you Googled this, which would be about 0.248. So pretty cool. Pretty cool that it works out so nice. But probably not something I expect you to do on the fly or catch at home. I don't know. Is it Ethan saying like, yeah, good call on that one. I don't think I'd be picking that one up off the fly. Yeah, that's kind of a nifty trick. Nor is it something I think I'd be likely to ask you on an exam for. That's just a nice little trick of algebra. Okay, let me pause. I'll put this in the notes for today. So if this went a little fast and you want to look at it a little slower, you'll see a copy of this in the notes. Comments or questions on this other than that it was really amazingly cool. All right, a couple of nods on that. Thank you. Extra credit for those nods. Appreciate that. So a lot of times, especially when you get higher and higher in math, you'll see people, they'll prove something and the proof lasts for pages and pages and pages. And to alert a sleepy-headed reader that they're done, they'll put this at the end of it. QED. It's a Latin term for quod erat demonstrandum, that which was to be shown or proved. And it's a way to say, hey, we finished. Now, I don't expect anyone to remember Latin in this class, so we got a better way of remembering a QED, meaning we finished the problem. In this class, it's quite elegantly demonstrated. So there you go. All right, all set for section 10.6 for now.